Hi, my name is Ryan Thompson, and this is my submission for question 9 of the final exam for CPSC 5210. So in question 9, we're asked to use this Dijkstra algorithm to determine the closest nodes in matching, or we're supposed to modify this to take into account not only shortest path, but take color into account as well. So here I've outlined some of the basic notation that we'll be using. So G is a graph, where V is the vertices and E is the edges. C is the unique, distinct colors of the graph, the count, and S is the starting node. And inside every vertex, V.C is the color of that vertex. W is a square matrix representing the edge weighting between each vertex. It gets a 1 if the edge is realized and the vertexes are different colors. It gets a 0 if the edges realized and the vertices are the same colors, and it gets a nil if the edges are not realized. So typically in other forms of this, W is just a 1 or it's just a series of integer values for this algorithm to work. Also a series of positive integer values. So the way that helped me think about this is, again, we're going to store the results in a matrix. So for each vertex, at each iteration, so at each going vertex by vertex by vertex, and leaving a different string behind, a different subset of vertices of the original total set, you can add the distances like we did here. You'll be either adding a 0, a 1, or a nil. And if you have a nil, that series is done. It's reached its terminal node, its terminal point. And now we'll have a series of total distances. And so we'll only need to fill this out once, and then for every single node, starting at S, starting at the original start node, you'll know what that distance is from there. So M has size n plus 1. For each element of the matrix, the value represents the distance from S from the current point to that iteration. So it's not that incremental additional value, it's the incremental plus the total distance up to and including that point. If a vertex is not realized, it's given the null, and you've reached the terminal point of that substring, of that subnode path. The matrix needs only to be calculated once for each S. So we're also asked to modify the relax function to have color as well. So here, color relax has node U, node V, and the weight. So given the U node and the V node, if it's not nil, so that it's a realized edge, we're going to add the weight at that element of the weighting matrix. And we're going to add it, again, because it's a cumulative runtime, we're going to add it to the total score. And then we're going to update the predecessor, which is pi in this case. So v.pi, or the predecessor, now is u. So now we know in that subnode path how we got there for that cumulative total. So here's the colored Dijkstra. Here's a colored Dijkstra example. So number of colors equals the distinct G.color, or the total color count. For each vertex in G.V, we're going to start it off at 0. Again here, so you're getting a 0 and a 0. And this is important because when you're doing the cumulative total distance, you need to start at something because you can't add something to nothing. So it's kind of just a programming formality. Now, we're going to start our sequence as the empty set. And once So once we set our sequence to empty, we set all the vertexes into kind of this holder array, Q. And while Q is not empty, we're going to do these below functions. So U, whatever node you're at now, we're going to extract it from the total nodes, the total vertices. We're going to extract it out and put a pointer to it. So it's not going to be eligible to be reevaluated because we've pulled it out of Q. Now for each V that's an adjacent or connected to U, we're going to evaluate it, and we're going to call this color relax. And we're going to store it in the M function. We're going to, not M function, this M matrix here, this M matrix. So M is going to get this total V.D, and then it's going to record you'll have the predecessor as well. So M will represent the total value. And it will go through and evaluate it. My implementation of this Dijkstra algorithm works on the Fibonacci heap. That's the main assumption. That's the assumption the book goes through with as well. So all of this nodes here would be the same, even if colors, except for this line, would be the colors regardless. Even if color wasn't a factor, this is the approach that I would do. So this is the additional stuff here, but this is also an interesting point of this algorithm that, and we'll talk about the time complexity that it adds, but just at the end, once we have this full matrix from the start node, we can go through and figure out. The question really becomes simple as to what is the minimum distance to get to a certain color. So now inside this algorithm, we'll iterate over the colors and we'll determine the subset of the color. So if the color is blue, say the first color, we'll say where is G.color blue, and then we want to go to the very last iteration here, which is the final cumulative distance in the matrix, and we'll look for which one is the minimum. So we have the full set of every node and every cumulative distance from the starting node. Now we're going to subset into that the ones that have a matching color to what we're interested in, and then we're going to record what is that total distance and what is that exact node. So in the end, C underscore node I will have the same number of elements as the number of colors, and C underscore D will have the same number of elements as the number of colors. And we'll do this for each color, continually looking to subset into it. So by the end, you've created enough subsets that the union of all the subsets is the full set again. That's an important point for the runtime that I'll point out later. Here in 9b, we're asked to evaluate the worst case runtime for the algorithm that I just explained. Well, since Dijkstra is implemented with the Fibonacci heap, and it has the lowest big O of all these path methods, where O is equal to the number of edges plus V log V, then the added time for color is any time to find the indices where vertex color matches. That's this substring matching here. And that's equal to theta V multiplied by the number of unique colors. And I say theta V because you're evaluating if it matches the color on every single vertex. So you're doing it every time. And you're doing it for V number. And you're doing it for the number of colors. So if there's 4 colors, you multiply by the number of unique colors by T color, or theta V. This is because every vertex will be checked every time. The next time that this color algorithm adds is the time to find the minimum of the color subset, T min. But since the summation of the subsets equals the total set, and the added time complexity is equal to iterating over each one, so log V. Because you're really looking over iteratively the whole thing. So as you're having to loop through each one, it's equivalent to finding the set of the total set. Because finding the minimum for a subset, say you have 100 elements and each subset has 25. Well, you have to go through 4 groups to 25 to find the minimum. And that should have the same exact runtime as looping through 100 elements and finding the minimum of there. So aggregating that approach mathematically will leave you with the log V time for a basic function. So we just tack on the additional time complexity for the for adding the color into it. So here the number of unique colors times the number that we have to search over to determine a subset, plus log V, because as you have to go through every one of them to find, as you have to go through the height of the entire tree to find the minimum value, it's equivalent to doing the minimum over a subset, over the however many subsets that you'll be required to do. In the best case running time for the colored Dijkstra with color relax, the best case runtime for a colored Dijkstra is equal to the worst case. I say this because the same time and memory are required because a full matrix M, this full matrix M with all the cumulative paths from the starting node, is always calculated because the full path is not known prior to the iteration. So for me, one of the points that at least theoretically justified this to me is that if you just take the first blue node that you hit, that may not, because of this matching scoring scheme, if you were to take the first blue node that you hit, it may be a value of 2. But if you iterate over the subsequences, over every vertex, there in theory could be a path of similar colors but it may take 15 nodes to get there. But because they're all similar colors, they all will add 0 to the distance based on this scoring function. And then you'll get to the blue. So you can wind up with a value of 1 as opposed to a value of 2. But if you don't calculate over the full path, you don't know that. And so you're still going to have these same time requirements, whether or not best case, worst case, because you have to know how these full paths play out. So the best case runtime and the worst case runtime, in my opinion, in my thoughts, in my thought example, are equal to each other.